Okay, my presentation is try to answer some of the questions on Vanderlei is about the prediction of the service life that now is very popular, and I have introduced initiation and propagation periods. The content, I will try to make a short analysis of the new trends that are included in the model code, FIB model code. This Congress also is traditional that commissions and committees of FIB are participating. We have now this model code with a probabilistic design of the service life, but I would like to analyze from the perspective of my work on the two RILEM committees that were dealing with this subject of service life, and some of the members that you are here will recognize part of our discussions in these two RILEM committees. And is to say that the service life, the needs the support, the engineering modeling needs the support of a deep knowledge of material microstructure and transport capacity due to the lack of the calibration we have, or the record we have, the long-term record we have on the service life. And I will try to illustrate shortly with some examples. The background, and I would like to recognize the discussions in these committees that I am now showing here. I mentioned already the TC on testing and modeling chloride transport into concrete, that we were studying the influencing parameters on the service life prediction, and also the other in which we broader the scope, and we were commenting on all kind of models like multi-scale modeling or numerical models about. Also the Duracrit project that has been an inspiration for the model code in the sense in the part of durability, because in that project that I was a member, we tried to develop the framework for the reliability concepts to be introduced into durability. But I would like to emphasize also, because sometimes it's very enthusiastically used, that the examples that are there are fictitious, that some of the numbers are invented, and they were tuned to just illustrate. It has an academic purpose, but some of the data are simply taken for the sake of illustration, and in that case cannot be taken as they are just the good answer. And finally, that now more recently, I am member of the Commission 5 of FIB on durability. They produced this Bulletin 34, that they introduced the models of Duracrit, but without enough calibration, and finally they are in the model code. Well, we have been talking the first days on the degradation functions, on the damage functions. Chris Gestrons the first day, and yesterday the other speakers were very well illustrating the importance of this degradation function in the total framework of the service life prediction. I have concentrated in this function. They appear first into this model, in the model for the initiation or incubation of the damage, and after the degradation, the developing of the damage, and we can just put in this other manner as degradation function, and in which we need to define, for the sake of design, limit states in order to obtain a residual life. And what is important, I will emphasize later, is, as has been illustrated by Alexander, is always the interaction with the ambient. In that case, we should have also models for the ambient, for the climate, that are now only concentrated in exposure classes. Well, the other aspect to be taken into account in this presentation of a background is that we are now in the trend to change the standards to be performance-based, the performance-based design. And we need to remember that concrete strength has been a performance property. You need to reach this. In that case, we have certain experience, or a lot of experience, because it was introduced in the 50s, the idea to deal with this scattering the concrete strength by a probabilistic treatment. And we are talking in the design about characteristic values. And now this trend is what is needed to be applied for the durability prediction, and this has to be an alternative to the design from the concrete misproportioning. But in this case, it's necessary not to forget the enormous experience and works that the people working in strength and structural performance have made. And in fact, this was the driving force for Duracrit project. Talking about or mentioning the model code, this is in FIB. I don't try that you just read this, because I just copy and paste, but this is the scheme in the bulletin for the durability design. And the most important is the parallel alternative paths. They describe several alternative paths for the verification, from the deemed to satisfy method to avoidance of deterioration or the probabilistic treatment. Just presented in another manner, we have in the future several possibilities for verifying the durability, several verification formats, the traditional one, the more modern with service life, deterministic or probabilistic treatments, and also durability indicators that I am not going to talk too much, but that the most important, they should give a similar result or equivalent results. We shouldn't go through this path having a completely different mixed proportioning than this one. Otherwise, it's not correct. It's what I am telling about calibration. We should be coherent and not to give too much differences. Of course, there are several types of concrete that can fulfill durability, but should be in the same range. And also, we need always a test to just give the numbers for the future performance, and a model in this case. And the concrete composition should be feasible. And I say feasible because I remember Great Belt project in which they were testing a lot of mixes that they were really very sophisticated. And also I will comment with Panama Canal that they had to make about 60 mixes for finding the optimum. In that case, we should be aware on the cost of the durability performance. It's more costly, and somebody has to take into account, and in that case to consider. About the model code, they are for the models. Yeah, because when I shift, I don't, okay. In the model code, we have as degradation or damage function for carbonation. This model I will not illustrate, only to say that is too much sophisticated, and this is one of the examples in which it shouldn't be taken strictly. The idea was conceptual when we developed this model, saying that the curing factor and the environmental factor, they should influence the performance, also the time of wetness, but when you try to give numbers, it's really complex to find the right numbers. In that case, this should be taken as conceptual. Even the resistance to carbonation was an idea during the project to try to be more psychologically close to the engineer by saying resistance, but this is the inverse of the velocity of carbonation. In that case, shouldn't be taken each by each. It's only a conceptual model. Regarding the chlorides, it was taking the error function from Fick's law, and the only is that we introduced, at that time we were also members of the TC, RILEM TC, that we were discussing the influence of the factors, and here is introduced the convection zone in order to take into account the maximum when the profile has a maximum. the other parts are the same. Also, there is an aging factor that is not in this equation I will talk about, and also the influence of the temperature. I will concentrate in chlorides because it's the most common model that is used. About this model, we need to consider, as was probabilistic treatment, that we will have a distribution of the surface concentration, a distribution of the diffusion coefficient and the aging factor, perhaps the convection zone with also a distribution, and a distribution of the position of the bar. In that case, for solving the equation in a probabilistic manner that you can do by Monte Carlo or other tools, it's necessary to have a mean value for each of these parameters: the initial chloride content in the cement, the surface concentration, the chloride threshold, the cover depth, the convection zone, diffusion coefficient, aging factor, and the time at which you are accounting for the aging factor, in which time you make the first test and the further test. And it's necessary to have the mean, the standard deviation, the coefficient of variation. Here there are, and I put in other color, the factors depending on the effect of temperature that I will not talk about, but again, this is conceptual. Really, when you have higher temperatures, if the concrete is not saturated, Arrhenius law cannot be used. Only can be used if you have a completely saturated concrete. Okay, just introduced in an Excel file for the probabilistic treatment or in another program. Here I present the sensitivity analysis of the effects of the different parameters in the model, assuming a chloride threshold of 0.4, but if the initial concentration is higher, really we are decreasing the chloride threshold. In that case, without aging in blue or black, and with aging factor of 0.5. And this is one thing. There are very, very important differences when we just tune or shift the values. In that case, it's very necessary to say all the numbers assume, otherwise you will have completely different probabilities of failure when you do. With aging, that is the red one, as soon as you have a high aging factor, in Spain is suggested 0.5 for all cases, really the probability of failure is very, very low. That means that the service life of 50 years, I think that I did this with 50 years, will be fulfilled always. However, if you don't have this aging, the effect of the different parameters, it can be seen here comparatively, is very high. For instance, the surface concentration, the thickness of the convection zone is not too important. The years of life, of course, is important, 50, 100 or 200, but the critical one is the aging factor. As soon as, for instance, with a low diffusion coefficient, you just introduce an aging factor, the probability fails completely from very high to almost negligible. And it's also clear here with a much higher diffusion coefficient of 25. In that case, this is the controlling parameter of this equation. And the other is here is summarizing. Aging factor is the critical one. Also is important the reference time at what you do the first test. It is 28 days or other time. And the duration of the application time. I think that here is one of the answers. We should limit the application. We cannot leave the value to be applied during the whole life. First, because maybe it's not true, And the second, because if we go, for instance, in this case, we have almost 1 order of magnitude of decrease of the diffusion coefficient with time if we let the aging factor to go until the end. If we just say only 10 years or only 5 years for the application or 1 year, that will be much more conservative, that is my recommendation, or much more at least less risky because of the uncertainties we have and of how this will evolve. About the surface concentration, what is very important is the consideration that the surface concentration is not the extrapolation of this maximum, because this is a virtual concentration, it is not there. The real concentration, RILEM TC on testing has was working on that in order to say that the maximum is what have to be taken as the driving force, as the surface concentration was incorporated into the Duracrit project. In that case, has to be there, and just to add this skin zone. But the thickness is important. And of course, about the chloride threshold is also important, as this is one of the discussions, which is the chloride threshold. First, we should imagine, as I have presented previously, the passivation not as a just point, but is a continuous evolution in which the area affected, if it is carbonation, will be the external part, the area affected around the perimeter will increase with time. In that case, the amount of damage will increase with time. In that case, the passivation is like a period of time, and the chloride threshold in that case is also a kind of statistical distribution. I just put here in red the distribution we found in mortar specimens in the lab, and this was found by Marqueset in the real breaches in Norway, and they are so close that we can say that this is a general distribution for breaches, at least in the aerial part, and we see that the 0.4 that we are typically using is giving about 10% probability of failure. In that case, taking a 0.4 as the usual value is conservative, is correct, is to say that it will be about 10% probability of depassivation in the time we are considering. Which are then the best values during the whole working life of aging, surface concentration and chloride threshold? Really, we cannot respond to this question now due to the lack of calibration of these models at long term. And this is what we need to assume. We don't have more record than 20, 30 years of following specimens and following structures, mainly for the aging, how they have evolved in the diffusion coefficient. However, we need to apply what we have now in real works, and this is the typical challenge of the engineers. We need to give an answer. We cannot wait 20 years to give an answer. Very briefly, to use this for illustration, the new locks are being built in parallel to the old ones. Really, they are building them in the two entrances of the two oceans, here in one side and the other side. The profile of the country is in this manner. They need to have the locks to go up and to go down because they have the artificial lakes and the lakes that are facilitating the navigation in the middle. And the new locks have a difference that they have aside in some pools in order to recover, to recycle the water and to spend less fresh water of the lakes. And as the capacity is much higher, they will just exhaust the hydraulic sources if they are using and just delivering to the oceans. In that case, they did that. And this is a view of the works going on. We took a course of the old canal that is now 100 years old. In this moment is this year celebrating the centenary. And we were analyzing and to study precisely how this has been aged. I presented a paper on the Aging Congress of Klaas van Breugel about these profiles. We have a scatter in the surface concentration and the maximum. The maximum also has different convection zones, and it's clear that in the logs that are near the sea, we have much higher concentration of chlorides. We are realizing that these amounts are similar to what we are looking in many other cases, and in the intermediate is much lower amount of chlorides, and of course in the fresh water of the lake there are not chlorides at all. We were analyzing the diffusion coefficient, the surface concentration, and so in order to make a statistical analysis. And I invite all of you that are related to all structures to try to collect. We need to collect data to have a statistical analysis of all structures in order to try to fill the gap we have on the knowledge. We didn't any test in this concrete 100 years ago, of course. In that case, we cannot relate the short time test to these values, but at least we can make some projection. Also, we lack, and it's important on the models for the ambient. We use the exposure classes, tidal, aerial and submerged, but we don't have models. I would like to mention here in Brazil the very good work of Gibson Meira, that in his thesis he has developed a model for the deposition of chlorides depending on the distance to the seaside, and he's continuing working on the effect of winds. There are now other people working on that. This is a first attempt, but we need more work on this area. And finally, to just go ahead and try to finish this part, is how to predict with this uncertainty. Being aware of the model limitations, this is very important to transmit to the engineers. We shouldn't be too much triumphantly saying we have a model code and we have a model, and now, no, we need to transmit also the limitations. And also they need to be aware that they should understand the physics of the chloride ingress and the evolution of concrete microstructure with age. Because if they are not able to understand a minimum, and we were talking the other day about the importance of the education on the engineers, it's better that they use the traditional manner. Because the new models are very attractive, they shouldn't go to that. And I say that because I am finding that the people are trying to make, in Panama Canal we had this problem. They just define a performance-based specification, but without any knowledge behind. And that makes a lot of problems with the builder. And if nobody understands the physics, after it's very difficult to try to convince the authorities or the owners that they were wrong in some parts of the specification. Well, the other is being conservative, making reasonable and conservative structural durability design. You cannot make a very strange structure or very slender or so if you are in a very aggressive media. It's much better to be conservative, in spite maybe the aesthetics is not so good, but after the maintenance and the problems maybe are too early. Testing concrete mixes is necessary to test for the durability and the periodic confirmation of the assumptions by monitoring or by inspection, just to be sure that the things are going as were assumed during the initial time, and collecting that data for better design. Test types. Well, I would like to express that I am completely in favor of natural diffusion when the responsibility of the structure is high. I find very many advantages, and in fact at European level this is the test that has been standardized as reference. As I will say, you can use other but not as reference. Why? It's the best we have, and mainly because it's able to just have the salt water in contact to the concrete continuously. Because if we need to study aging, we need to have maybe even 1 year long periods and of contact, and it's necessary to have the salt water in contact permanently. It is an integral test in the sense that is giving the performance and the chloride after the chloride has been acting continuously on the concrete. The concrete ages in presence of the salt water, and also is allowing a correct binding of chlorides. Is possible to have the surface concentration from the chloride profile and also the threshold value. In that case, I think that is the most suitable test for the testing of the mixes, in spite that it takes a minimum of 90 days, or even for aging should be longer. I am against of using the accelerated test, whatever is, if we go to the aging factor, because in this case the concrete is aging out of the salt solution. You just leave the concrete, and after a certain moments you just measure, because if it is in contact to the salt, you cannot use these methods. Well, because maybe this one on the coulombs, but you are removing the chlorides that have been entering in contact to the salt water. In that case, you cannot use these methods for the aging, and aging is the controlling parameter. This is a differential method that do not enable chloride binding during the short time of the testing, and no values of chloride threshold are given, or the surface concentration are obtained. I am in favor, as several of you know, of the resistivity, because if you like really a quick, a very rapid method, resistivity is non-destructive, is able to give the same information as the other methods, and however, you can leave the concrete inside the salt solution and follow the resistivity after several times in contact the concrete with salt solution. We have developed a model for the initiation period based into the resistivity and the relation with the diffusivity, and also the resistivity and relation with the corrosion rate. In that case, it's possible using a square root law to have a service life model based into the resistivity measured at 28 days, and for aging it's possible to live in contact to the salt water and have the aging factor correctly. It's a non-destructive method. It can be used in the lab and on-site. We have used to verify the resistivity into the Panama Canal in order to know how has been fulfilled. It facilitates routine quality control and can be used for calculating service life. And also it has a correlation with the ASTO test, the coulombs, that is about 200 ohms meter is equivalent to 1,000 coulombs. And this was, we published with David Whiting in 96, this equivalence. And about the aging factor, is possible just monitoring the increase of resistivity with time. These are different mixes in Panama Canal with the aging factors, and we compare the aging factors of the resistivity with those of the ponding test, having the salt water in contact with them. And the aging factors obtained this manner are very, very similar to have the concrete in contact to the salt water longer times. This was until 120 days, that was the specification. Well, I go now to end with the propagation models. Again, we need to try to develop a model for the damage model for the propagation of the corrosion, and also taking into account the effect of the environment. Is not going now. Well, the model was published time ago and is very simple. The amount of corrosion that is reached after a certain time depends on the velocity of corrosion, of the corrosion rate. I mean, millimeters per year of penetration of the corrosion by the years give the millimeters after this time. And this is the most simple one, just measuring the decrease in the diameter Also, it's possible to measure the pitting factor that we introduce as an alpha and apply to the diameter, the initial diameter minus the penetration at a certain age multiplied by the 10 times we suggest for the pitting factor for the most deep pit will give us the residual diameter after a certain time. Is that happening in reality? This can be predicted in some manner, not only saying that this is the simple model. Well, yes, the corrosion is dependent on the amount of liquid water in the concrete, that is of the degree of saturation or the volumetric fraction of water. In that case, if we are able to collect or to measure the amount of water remaining in the amount of water remaining in the concrete depending on the ambient, it will be possible to have the degree of saturation, and from the degree of saturation we can have finally the corrosion, as I will show. Here I would like to illustrate the effect of temperature that I was just mentioning yesterday. In concrete, when the temperature rises, the water inside evaporates. In that case, this is a type of curve that I took from atmospheric corrosion. It happens exactly the same than when you have steel in the open atmosphere. At the beginning, as it is wet, you have a layer of water on the steel, the corrosion rate increases. But as soon as the water evaporates due to the rise of the temperature, the corrosion rate decreases. And this is why it's complex to introduce the effect of temperature in the corrosion rate, because it has a opposite effect depending on the length of the time and the increase in temperature. That is conceptual. Finally, if it is dry, it is not corrosion. And this is what happens in the south of Europe, in my country, because we have dry periods, long time. In that case, in spite of high temperatures, we have less corrosion than the Nordic people, that they have much more time of wetness due the water remains inside the pores longer time. Just going into the effect of the ambient, we did a lot of work on this, and the corrosion rate changes, of course, depending on the rain events, on the temperature, and so. But if we just plot that as accumulated corrosion, that is the amount of loss in the diameter with time, that is not so dispersed. It is progressive, of course, the loss in section, and in that case, going into the events of summer and winter, it's possible to have more or less what is in the conceptual model of a constant corrosion rate. In that case, just this is the P-core that we were commenting at the end. At each age, you collect a loss in corrosion that has depended on the corrosion rate, but as the annual cycles of climate repeat, that is cycled and is continuous. And finally, just using a modified version of Archie's law that has here the degree of saturation of the volumetric water just powered by a factor that can be 2 as a average, and using the model that we developed of the relation of the corrosion rate with resistivity, we may have this for the prediction that is a constant, is a fixed number, the volumetric fraction of water power to 2, for instance, and the resistivity of the pore solution that also changes not too much by the time of the acting of the corrosion. And this is the model based in the degree of saturation of the volumetric water in there. Finally, I finish with it, which is the acceptable limit state for the probability of corrosion, that is other question addressed. In that case, it's necessary to make the structural calculation. You need to verify the serviceability limit state, the ultimate limit state with structural engineers. They need to to work with you, at least with me, that I am not structural, in order to calculate the loss in cross-section from the accumulated corrosion. We just link this loss in cross-section with the 4 main consequences of the corrosion into the structural performance, that is the loss of the diameter, the loss of ductility, I will say how much important is this one now, the loss in the bond, and the cracking. On all those effects that have to be analyzed independently affect the full structural performance of the corroded elements. I finish with Maracanã Stadium, being in Brazil and having had the World Cup. We should talk about. Here I need to talk about Ennio Pacini, Professor Ennio Pacini, well known here, is not in this Congress, is Professor of Goiás, and he was who diagnosed correctly what happened in the, let's say, all Maracanã Marquezine that was not showing any sign of corrosion apparently, but as soon as you touching with a hammer, the cover was falling down, and the inside showed that almost all the rebars were corroding. They have done this reinforcement in 2006, and it was very difficult to convince the federal state of Rio de Janeiro that they had to demolish the Marquesina. They were not thinking the need of demolish the Marquesina, because the risk of falling down was very important, as said by the structural engineers. What did Ennio? He was trying to make a detailed diagnosis using ultrasounds and using the corrosion rate meter, and he detected very weak zones non-destructively and also high corrosion rates, and that is when he was suspecting that the problem is much bigger. And also we realized that the steel is not only corroding and just losing the section, but you can break the steels with the hands. This is one that we broke there because it has been embrittled, and corrosion can embrittle the steel when you have losses higher than 25%, and this is a hidden problem that we shouldn't forget when we are repairing the structures. Well, the final comments for the initiation period, there are degradation functions, but still lack of long-term calibration. We have them, but we need to be aware on that. There are application needs understanding of the physical process and concrete microstructure should be applied by people being aware on that. Models of climatic events and their impact in the degree of concrete saturation are needed. We need those for knowing more how is the degree of saturation depending on the different climates. And about the propagation period, the model is less uncertain, has been studied much longer with the aging. We know how the steel corrodes and how the different structural consequences are affected, but we need also the climatic data and the concrete water uptake for the prediction, because we need to have the degree of saturation. And about the structural consequences, the verification of limited states, we need much more work. There is necessary, now there is an expansion of the interest in this, on how corroded structures perform, and this is very important to collect data and to continue making work. And finally, well, this is Maracanã Stadium, and it said, I received a book saying that Maracanã is for the 21st century. I hope that they reach also a very long life for this new, in my opinion, more beautiful stadium. Thank you.
We can take a couple of questions. Carmen, first of all, thank you very much for the great presentation, which answers partially the question I asked on the first day of this event. Continue on the aging factor. You present some numbers now, which I think is an evolution based on the discussion we had some time ago on the European standard on concrete level. But those numbers, are they taken for OPC type 1 cement concrete? Which kind of cement are you assuming?
Values I show there were for the Panama Canal mixes, and they were
the previous ones, because you also showed some with chloride on the slide.
Well, typically they change from 0 to 0.8. That are very typical. But of course, to say 0.3 or 0.8, they can be a huge difference in the prediction. In that case, I think that this should be tested. In fact, we are discussing in the committee you were in Europe, we are discussing how to introduce the testing of aging in our present standard, whether to test until 1 year or how to test. And if you don't have, you need to be conservative. Not to use high values. I would rather prefer even 0.5. I think that is very high as soon as you make a sensitivity analysis. But the first is to measure real values or use conservative values.
Yeah, yes, I understand, and I think that's the point. But conservative values, what would it be if I have a cement type 1 or type 3? I think what you say conservative might be...
Conservative for type 1 is almost 0, because there are some of them that they don't have aging, almost not aging, because they are completely hydrated after the 28 days, and only when you have the contact with the salt water, you have a refinement of the pores due to the precipitation of the Friedel salt. In that case, you may go to 0.05 or 0.1. And for type 3, a conservative value may be between 0.3 and 0.5, because CEM3 has a very high aging factor.
You mean the binding of chloride?
Well, stopping the penetration of chloride, so binding, yes, not allowing the profile to go ahead.
Okay, so only if I can ask another question, or yeah? In lab, the degradation of concrete happens in a very clear way. You can measure sulfate, chloride, carbonation separately. But in nature, those things, they might happen at the same time. At the European level, I know you are very active on that. Do we have some discussion on tests that could measure those degradation factors together?
Well, you need to measure in the same... I mean, when you have chlorides, you have usually saturated concrete and you don't have carbonation, or the carbonation is negligible. But if you are in a condition where you have both, you need to make the chloride profile and after to measure the carbonation. But the treatment for the degradation functions are different, should be different. You need to calculate whether the front of carbonation will reach the bar before or after the chloride threshold reaches the bar. And after work only with the predominant or the most quick process.
Okay, thank you.
Okay, thank you, Carmen. It was an excellent presentation. And I think it's, you mostly discussed chloride. And of course, there are a lot of offshore structures in front of the ocean. And that's important. But and how about carbonation and because this is really the bulk, and carbonation, and also after the initiation period, what goes the corrosion rate, and you think there is something that should be done? Can we still use these accelerated carbonation tests, or because it's what people are doing?
Yeah, well, sorry, thinking in the time, I had to concentrate, and thanks again for the questions. The carbonation is much less affected by aging factor. That is clear. You may have a first period for the skin of the concrete, but after It will depend on the humidity, whether you have the square root of time or it's not the square root of time. If you have higher humidity, you will have less velocity of carbonation. In the case of Maracanã, it's very particular. It was for me very interesting. Rio has 80% relative humidity all the year, at least the weather that was supplied to me, and the temperature is high. And I was thinking, in the typical values we have 80%, we shouldn't have carbonation. It's 60 years old and was carbonated very much. And the explanation I found with Ennio, we found is a porous concrete. In that case, this water that is there, it has mainly capillary pores and bicapillary pores. In that case, this water is allowing enough empty space. In that case, 80% is not saturating the pores, and if it is not saturating the pores, the CO2 can penetrate. Because we had there is the worst condition, is the more carbonation and high corrosion. Corrosion rates of 3 and 5 microamperes, 30 and 50 micrometers per year, that are very high, we found there in that case. In that case, this is important, as you say, in all the coast, but this, in my opinion, well known. I mean, we know the rates of corrosion with the degree of saturation. We know the more or less with an accelerated test. If you are using OPC, you can use. If you are using blending materials, you cannot use accelerated methods. We are in favor, in the European standard, we have a natural diffusion test, and the only is that they have decided that is 1 year. It's too long for me. In my opinion, we should have a number at 3 months. If you don't have carbonation, it's because it's a good concrete, and wait until 1 year to have some millimeters or more for having a velocity, a number. But natural diffusion is the most convenient. I know that it appears that it's too long and so, but this is too long to discuss here.
So you think it's just since the pore size distribution controls the amount of water in the surface area, so this is crucial on the after the initiation period. If you have larger pores, you can even go in high humidity, then you're going to have carbonation, and that's high humidity, you're going to have a very high corrosion speed.
Yeah, this is the lesson we deduced from Maracanã case.
Okay, thank you.
Thank you. I think we'll close the session. It's very interesting. We'll certainly have a lot of comments for comment. Please come back at 10:45. We have another very interesting session. We have 2 star speakers for you, Karen Schreibner and Roberto Torren. So please do come back 10:45 sharp.